Greetings and welcome back. For this video, we're going to look at Newton's three laws of motion, and we're going to be looking at the notes. There are three parts, one part for the first law, another part for the second law, and a third part for the third law. If you would like to skip ahead to the second or third parts and laws, you can click on the links here on the screen and it'll take you directly to those parts. Otherwise, we're going to start with law number one and go straight through. So the first thing we talked about was, who is Newton? And according to a book written by Michael Hart in the 1970s, Michael Hart listed the 100 most influential people of all time. And according to this list, Isaac Newton was number 2. He was right behind the Prophet Muhammad and before Jesus Christ, Buddha, Confucius. We also have on the list St. Paul, one of the apostles of Jesus, Kai Lun, who invented paper, Gutenberg, who invented the printing press, Christopher Columbus, who discovered America, the European discovery of America, and Albert Einstein. And so what did Newton do to deserve second among all these other religious leaders like Buddha and Jesus and Muhammad? And Newton did a few things. He did discover gravity. So he realized that the gravity that pulls things down to Earth is the same gravity that keeps planets in motion around the sun. So there's the same forces involved there. Newton also discovered the nature of light, that light can be broken up into all the colors of the rainbow, the Roy G. Biv. That was Newton. Newton also invented calculus. So anything that we do with calculus, that is due because of Newton. And so Newton had many influences. He invented the telescope, so credited for that. And he was just an absolute genius. In my opinion, one of the smartest people who have ever lived. The guy was absolutely brilliant. So the first thing we're going to talk about is mass. And the symbol for mass is an M. And mass is the amount of matter or stuff in an object. It is the number of protons, electrons, atoms. It's actually how much stuff is present there. And the units are kilograms. So we could also use grams for this, but it will be kilograms. And the mass of an object does not change unless it gains or loses stuff. So if something has a mass, for me, for example, if I have a mass, which I do, in order to change my mass, I can either gain mass by eating or drinking more. I can lose mass by cutting my hair, cutting off a finger or something like that. I would lose mass. But if I go someplace different, if I go to outer space or I go to the moon, my mass stays exactly the same because I have the same amount of molecules. The next point was force. And a force is simply a push or a pull. And a push is exactly the same as a pull. It's just in a different, from a different direction. The units are measured in newtons. So we're going to be using newtons for forces. There's another unit which we can use, and that is kilogram meters per second squared. So we'll sometimes use that instead of newtons when really they are the same thing. And we talked about friction. We talked about how friction is a force, and we emphasize that. Friction is a push or a pull. Let me highlight it as well. And that push or pull, that force, resists the motion of an object. So if something is trying to move, friction will push it and make it stop moving, basically. It acts in the opposite direction as the pushing force. And so I have a lovely picture here of a man pushing a lawnmower. And if he's pushing the lawnmower in one direction, the friction force is going to be pushing in the opposite direction. Friction is usually caused by rubbing. So when things rub or dragging, that's going to cause friction. And it slows things down and it makes things stop. So because of that rubbing, because that force, it's going to slow things down, make them stop. And we have that it generates heat. And this is a reason why matches work. The match, you're dragging it across. It's creating lots of friction and enough heat to actually catch the head of the match on fire. Inertia. Inertia is an object's tendency to resist a change in motion. So objects don't want to change. And so this was our book definition, and I came up with a Freitas definition. And my Freitas definition is stubborn. So things that have inertia are stubborn. They don't want to change. They're kind of lazy. And some things that have more mass have more inertia, and less mass has less inertia. And I talked about a demonstration that someone can do, and I used to do it. If you have 2 rolls of toilet paper, and you have a big roll that's almost full, and you have a smaller roll that's almost empty, and you tear off a piece of the big roll will not move very much because it has a lot of mass, a lot of inertia. It's very stubborn. It doesn't want to change. But the little roll, the roll that's almost out, sometimes when you pull it off, it spins and it unravels lots and lots and lots. And that's because it has little mass, little inertia. It's not very stubborn. It makes it move very easily. So we have an example here. It says which has more inertia and harder to push. And we have a picture of a truck and a picture of this strange topless guy pushing a smart car. And the answer is the truck. The truck has more mass, it has more inertia, it is more lazy, it's harder to push, it doesn't want to move. We also said the opposite could happen. If we have a truck and a skateboard, and they're both going at 5 miles an hour, which would be easier to stop? And the answer is the skateboard is easier to stop. Even though both are going 5 miles an hour, it's easier to stop because it's only, it has less mass, less inertia, it's less stubborn, and so it's easier to stop it. And the more mass, it's more lazy, more stubborn, more inertia. It just wants to keep rolling. Which takes us to Newton's first law, which basically talks about inertia. It says an object at rest stays at rest, and an object in motion stays in motion unless acted on by an unbalanced force. So if we have a book sitting on a table, the book will want to stay at rest, and it'll want to keep staying at rest until a force pushes it. And likewise, if I throw a chihuahua in outer space at 20 miles an hour, the chihuahua will float in a straight line at 20 miles an hour forever. It wants to stay moving. The only way it's going to stop is if something pushes it and makes it stop. All right, so here are 2 other examples. I don't think we did these in class, but they're here. Moops is driving too fast and not wearing a seatbelt. Use Newton's first law to explain what is going to happen if he crashes into a tree. So because Moops is in motion and the car is in motion, they want to stay in motion. So when he hits the tree, the car stops, but because he was in motion, he wants to stay in motion, he's going to fly straight through the windshield. The second one, Meeps just entered an elevator and pushes the button for the 9th floor. Use Newton's first law to explain why she feels herself being pushed towards the floor as the elevator begins to move upward. So she enters the elevator, she's at rest, the elevator's at rest, she pushes the button, the elevator starts to move up, but because she's at rest and wants to stay at rest, she's going to stay there, and the floor of the elevator is literally going to push into her feet, which makes herself feel heavier. All right, let us take a look at Newton's second law. Newton's second law, we start with weight. And weight is the force of gravity on an object. And we do want to emphasize that it is a force. So it is how much gravity is pushing down on you. And we said if you stand on a scale to measure your weight, what you're really measuring is how hard gravity is pushing down on that scale. Because if you push harder on the scale, it's gonna go harder. All right, sorry about that. I had to briefly pause it. Okay, moving on. So yeah, so basically, if you push down harder on the scale, it's going to weigh more. So weight is actually measuring how hard you're pushing down on the scale. The units are newtons for weight, and this is because weight is a force. Force is measured in newtons, so weight is measured in newtons. And we said that weight can change if you go someplace that has more or less gravity. So if you go to outer space, you're floating. And if you put a scale that's also floating right next to your feet, you would weigh 0 because there's nothing pushing your feet onto the scale. So you're not going to weigh anything. Likewise, if you go to a planet that has more gravity, you could weigh more than you do on Earth. We also have an equation here for weight. Weight equals mass times gravity. We said these problems are very, very easy, and one of the reasons they're very, very easy is because we know G is equal to 10 on Earth. So this number G, or this letter G, is just going to be the number 10. So that's going to make those really simple, and we're going to do an example right after we talk about mass versus weight. So mass and weight are very similar, and so to help us keep them straight, we made this little graph here. The first two things in here, in the first row, are talking about the definitions. Mass is the amount of matter. It's how much stuff is there. And weight is how hard gravity is pushing it down. The units for mass are kilograms. The units for weight are newtons, so that's a good way to tell them apart. And mass does not change based on your location. So as a student inappropriately said today, if you're fat here on Earth, you are fat in outer space. Your mass does not change. If you have a lot of atoms, those atoms are going to stay with you if you're in outer space. Your mass will not change. However, your weight does change and will change if you go to outer space. If you go to outer space, you have 0 weight. That is the ultimate weight loss. Lose all your weight, just go to outer space. You'll weigh 0. All right, let's do a quick example. We're actually going to do 2 of them. For this first one, we're trying to find the weight. So I have what is the weight? That's a question mark. I have 60 kilograms. We just said kilograms was a mass. So weight equals mg. It equals 60 times 10, which is 600 newtons. Easy, 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 very easy. These problems are not going to get any easier all year. We're going to do one more example. What is the weight? 70 kilograms. Kilograms is a dead giveaway. That is a mass. 20 meters per second squared. That is the gravity. So weight equals mg. Weight equals 70 times 20. Weight equals 1,400 newtons. Once again, easy peasy lemon squeezy. Very, very simple. Just multiplying mass times gravity. And this brings us to Newton's second law. Newton's second law says F equals ma. It's an equation. And so the first law says objects at rest stay in rest, objects in motion stay in motion unless acted on by an unbalanced force. This is saying exactly what happens. If it hits an unbalanced force, it is going to accelerate, which is why we have that A there. And so in other words, things will accelerate when there's an unbalanced force. So if the forces are not equal, things go faster. And so let's look at a few examples. If I have a picture of a car, and my car is going 100 meters per second, and I push it 20 newtons this way and 20 newtons this way, the car will stay the same speed. And this is because this force is balanced. These forces are balanced. And so because these forces are balanced, it's not going to go any faster. It's going to keep going at 100 meters per second. The car's not going to speed up, not going to slow down. There is no acceleration. A is 0. If, however, we look at a car, and the car is going 100, like it was in the last one, and we push on this car 20 again, and this time we push 8 this way, now this is an unbalanced force. Now the car will speed up. So we're pushing it, this car is going to accelerate, it is going to accelerate in a positive direction. So it's going to go from 100 to, 101, 102, 103, 104, 105, 106, 107. It's going to keep going faster and faster. And if we have a car, and it's going 100, separate this, and it gets pushed 20, and it gets pushed 30, this car will slow down. So it's going 100 to the right, but because the force is stronger, that 30 is stronger, it's going to slow down the car. It's going to keep slowing down the car until the car stops. And then if you keep pushing like this, the car will then, it will move backwards. So the car will eventually go to the left. All right, so I hope that makes sense. Let's look at an example. Moops pushes Meeps across the floor, accelerates her 2 meters per second squared. What force must he apply if she has a mass of 8? So I'm just going to write those down. 2 meters per second. What force? And 8 kilograms. Meters per second squared is my A. This is my M. F equals ma, which is 8 times 2, which is 16 newtons. And let's look at one more example. Moops pushes a 4 kilogram box with a force of 12 newtons. Meeps helps and pushes in the same direction with a force of 10 newtons. What is the acceleration of the box if there is 2 newtons of friction acting against the box? So once again, I'm just going to start writing what I know. So first I know the mass is 4 kilograms. I know there's a force of 12 newtons. I see a force of 10 newtons. I see what is the acceleration. And I see 2 newtons. That's another force. And so I know I'm going to use F equals ma. And I know m is 4. And a is my question mark, so that stays a. But I have 3 f's. And I only need 1 for the equation. So to explain this, if I draw a picture, I have my 4 kilogram box. Let's use a different color, make it a little bit more visible. If I push at 12, and Meeps pushes in the same direction, 10, and I have 2 newtons of friction pushes this way, my total force is really 12 plus 10, because they're pushing in the same direction, and we subtract the 2, because it's going in the opposite direction. So we get 20. And that is what we're going to put in right here. And now we can solve this. We can divide both sides. We get A is 5. So that was a little harder. But still, I don't think too bad. I think we can get it. Okay. Next concept, directly proportional. Directly proportional states that if one thing goes up, the other must go down. Sorry. If one goes up, the other must go up. I can read, I swear. The opposite is also true. If one goes down, the other must go down. And some examples we talked about. The more you work, the more money you make. Work goes up, money goes up. Or, more you exercise, better shape you get. Exercise goes up, your shape goes up. And in our physics world, this is with force and acceleration. So the harder you push something, the more force there is, the faster it speeds up, the more acceleration there is. And we can see this because the variables are on the opposite side of the equal sign. So when we have our equation, it's not popping up here. F equals ma. The F and the A are on opposite sides. So if F goes up, it's no longer equal. A has to go up to keep it equal. We also have the opposite, which is inversely proportional. Excuse me. Inversely proportional says if one goes up, the other must go down. And so some examples, the more you shop, the less money you have. Shopping goes up, money goes down. The more you drive, the less gas is in your car. Driving goes up, gas goes down. And in our physics world, it is mass and acceleration. If mass goes up, acceleration goes down. And you can feel this in your car. If you put a bunch of people in your car and the mass goes up, your car slows down. The acceleration, not as quick, not as much. And mathematically, this happens because they are on opposite sides of the equal sign. Sorry, they're on the same side of the equal sign. So because we have M and A on the same side, if M goes up, A has to go down to balance it because they're on the same side. So if one goes up, the other has to go down. All right, the last section and a short section is on Newton's third law. Newton's third law of motion states that, oops, not that, let's back up. Newton's third law says that for every action, there is an equal and opposite reaction. For every action, there's an equal and opposite reaction. And these forces, these actions, are equal in size, but opposite in direction. And we have a few examples of this. One example is birds. When they fly, birds push the air down, and the air pushes the birds up. So the harder the birds push down, the harder the air pushes the birds up. If I lean on the wall, I put my hand on the wall and I lean at an angle, I'm pushing on the wall pushes back on me. If the wall didn't push on me, I would fall straight to the ground. And if the wall pushed me harder, I would fly forward. So they're equal. Equal in size, opposite in direction. And we saw this in class. We had 2 office chairs, with wheels. And we put people of equal size on them. And we gave these people a rope. And we had only one person pull. If the person on the left pulls, it's going to bring, let's erase that. It's going to pull both people together. If only one person pulls. And the reason, let's say this person pulls. If this person pulls, they're applying a force and pulling this person towards them. And even though this person, number 2 over here, we'll label number 2, even though person number 2 does not pull back, they're just holding onto the rope, there's that opposite force that has to happen that's going to pull person number 1 over here towards them. So it's going to pull both people towards each other. And we also saw that we could also do this with heavier people and lighter people. So if we use someone who's heavier, so let's say this person has a belly and it's heavier, both people will still move, except this person will move less because they have more mass, belly, and this person is going to move a lot more. So they will not meet in the middle. They're going to meet towards the heavier person. But the forces are always equal. That is the key. In fact, maybe we should underline that. We should emphasize that. Let's emphasize it. Equal. And in fact, in your notebooks, we wrote in huge letters, forces always equal. Big, huge letters. Highlight it. Put stars next to it. Very, very important. Forces are always equal, but they're opposite. So, last slide. Whew. Last slide. A parked Volkswagen Bug is on the railroad tracks and a train is coming. Is the force on the car bigger, smaller, or the same as the force on the train? So let's do that part first. The forces are equal. The car hits the train just as hard as the train hits the car. The forces are always equal. The difference is this acceleration. So is the acceleration of the car bigger, smaller, or the same as the train? The acceleration is bigger. And the reason the acceleration is bigger is because the car is smaller. So because the car is smaller, it's going to fly when it gets hit by the train. So the bigger train is going to slow down a little bit. The car is going to go flying. So the acceleration is different, but the forces are always going to be the same. They're always going to be equal. All right, that is it for our notes. Hope you enjoyed them. Please watch them again if you don't, or feel free to ask me questions, send me an email, and I'll be happy to clarify for you. Thanks for watching.